Good morning, my name is Marco Sterlini and I am a master's graduate in mechatronics engineering from the University of Trento. I am presenting the results of my thesis on event-triggered methods for reduced function evaluation in neural network controllers. This research is the result of an internship conducted in collaboration with La CNRS laboratory in Toulouse in France. Neural networks are increasingly used across various fields, but their application in automatic control lacks the stability and safety guarantees needed for industrial use. This thesis tackles these challenges while reducing computational demands, enabling deployment on lower-end hardware. The system studied is a general Lure system with input saturation and constant disturbance, controlled by a multi-layer perceptron in closed loop. The network receives the plant state as input and outputs the control signal to stabilize the system. Stability of the closed-loop system is ensured through linear matrix inequalities conditions. To handle the nonlinearities in both the plant and the controller, sector conditions are used, allowing the analysis to focus only on the bounds of these nonlinearities rather than their exact form. To reduce computational load, a layer-wise event trigger mechanism, ETM, is designed, allowing each layer of the network to update independently based on locally computed conditions. If no trigger occurs, the layer reuses its previously stored value, saving resources. Triggering is based on violations of sector conditions, which helps limit conservatism. Additionally, a dynamic threshold is introduced to further relax the triggering criteria and reduce the frequency of updates. Triggering based solely on sector condition violations resulted in frequent events. To address this, a technical result inspired by Finzler's lemma was introduced to restructure the triggering matrices, promoting a more uniform triggering pattern. Stability is ensured through Lyapunov-based suffusion conditions, along with the linear approximation of the region of attraction. Numerical simulations show the state converging to the equilibrium, with each event in a network's last layer prompting a change in the control input. The resulting non-smooth trajectories are a direct effect of the event trigger controller, which nonetheless ensures exponential stability. In conclusion, this thesis presents a framework for designing layer-wise event-triggered mechanism for neural network controllers, enabling asynchronous state updates across the network. This approach integrates control theory with AI techniques such as reinforcement learning to train these neural network controllers, resulting in significantly reduced conservatism and nearly halved update rates compared to existing methods in the literature. These findings have been formalized in a conference paper accepted for presentation at the upcoming NOLCOS conference in Reykjavik in this July. Thank you for the attention.